Good evening, George Notchik here. About a month ago, I presented this problem involving an infinite grid of resistors of equal value throughout the grid. And I showed how to solve for the equivalent resistance between any two adjacent nodes in the grid by invoking a symmetry argument. And then I posed the question is, what would be the equivalent resistance if one looked at opposite diagonal nodes on any particular square? Like, for example, going between here and here. What would be the equivalent resistance? Remember, this network extends out infinitely in all directions. And I have been asked, why can one not use symmetry arguments for finding that particular equivalent resistance? Well, the short answer is it won't work, because if you try to use the symmetry arguments to solve for the equivalent resistance on the grid diagonal, you'll eventually get into trouble trying to satisfy Kirchhoff's voltage laws and Kirchhoff's current laws in the loops and nodes the further you become removed from the node where you're injecting the current. And I'll show you how that happens. And suppose, let's invoke the symmetry argument like we did, where we're going to inject a current I into this node with a current source. Well, we showed that by symmetry, remember this is extending out in all directions, so we can argue that the current is going to split equally when we inject it into the node. It's going to divide by 4 and go through each of these particular branches. Now, then, if we try on the next node to invoke the symmetry argument and say that this current coming into this node now is going to split equally in 3 different directions, it looks like that might be a reasonable assumption to make. If we try doing that, we're going to run into trouble. Now, to make this easy on the analysis, let's assume rather than current I going in, we have a current of 12I. Then when it comes here, it divides equally in 4 different directions. That's always true. So this now becomes 3I going in each direction. Now let's invoke symmetry when we get to this node. Well, the 3I is going to divide equally in 3 different directions, so each one of these currents will be I. Now, let's use Kirchhoff's voltage law. It must be satisfied in every loop of this network. So, if we go say around this loop, well, let's look here first, is we have this current 3I. Now it's also going to divide 3 different ways using this symmetry argument, so that is also I. 3I is coming in, then 3I is going to leave, a total of 3I, so we have I going in each direction here. Now, with Kirchhoff's voltage law, we can see that it's satisfied in this particular loop. Each one of these resistors have value R, so the voltage going from this node to this node will be 3I times R plus I times R, or 4I times R between here and here. And if we go around this way, we get the same value. We have 3I times R plus I times R, or 4I times R from here to here. So Kirchhoff's voltage law is satisfied there. Now, we see coming into this node now, we have two currents. We have current I and current I. So we have 2I coming in. We have to have 2I leaving by Kirchhoff's current law. So these two resistors are identical. So the currents have to be I leaving. Well, that being the case, let's look at Kirchhoff's voltage law going from this node to this node. Going in this direction, we have I times R plus I times R, or 2I times R, as the voltage from here to here. That also has to be satisfied going around this loop. We have I times R, so this also has to be I times R to give us the same voltage around the on this branch is the same as this branch, so that the sum of the voltages around the loop is 0. If we go around, we have IR plus IR minus IR here, so this has to be a minus IR. So the I has to be going this way. That is, voltage from here to here is IR plus IR, or 2IR. Voltage from here to here going around this path is IR plus IR, or 2IR. So now it's satisfied. Now, what happens when we get, say, to this point here? If you look, we have a current I coming in and we have a current I leaving. There's no current left to go into these two resistors. So the current in these resistors are going to have to be 0. We have the same problem now if we go this way. We have I and I coming in, so we have to have I leaving and another I leaving. Then Kirchhoff's voltage law going around these two paths from here to here, we have I times R plus I times R, or 2IR from here to here. So we have to get the same value going this way. Well, in order to do that, we're going to have a current I flowing here and an I flowing there. Well, right now we see we're getting into big trouble because we have a current I flowing in, we have 2I flowing out. So in order to satisfy that, the current in here is going to have to be in this direction, and to give us I. So we have 2I in, 2I leaving. But what happens when we go around this loop? Well, these two voltages cancel, so from here to here is going to have to be 0. In order to get that, we're going to have a current I flowing this way. And again, we're going to start running into big trouble. You can see that the currents have to be leaving towards infinity. We can't have currents coming back in this direction because the potential differences get less and less as we tend out towards infinity. But if you continue in this manner, you'll see that you'll be running into trouble the further the way you get from the injection point. Kirchhoff's voltage laws and current laws will start failing, and you'll will not be able to satisfy Kirchhoff's voltage laws in the loops or the current laws at the particular nodes. So that's the reason why it breaks down when you try to invoke symmetry to see how the current divides once it divides by fourths. After the injection point, you get to the next node from the injection point, and you cannot invoke symmetry. It's just not going to work. I'm going to show you now something to consider that might help you solve the problem. Now let's see how the current actually divides in the network. Here is our infinite grid. I'm not going to draw the symbol for the resistor is the squiggly lines. We can imagine that between any of the grid points, grid nodes, we have a resistance of value R. Now, we're going to inject the current in the center. So at this point, we have a current source injecting current into the network. We know by symmetry argument that that current has to divide equally. Now, the voltage at this node, this node, this node, and this node have to be identical, because we have identical resistors in each of these branches. We have identical currents, so the potential difference going from this node to this node has to be the same going around. So we know that those potentials are the same. Now, let's look at the current division on the next step. On the next step, this current's going to divide, but it's not going to be necessarily equal. It'll be equal here and here. This current will be divided equal here and here by symmetry. We can invoke that much in the symmetry. We know that these currents will be the same by symmetry. But the current that's leaving here is not the same as the blue. I'll designate that as green, because this is not a symmetrical division. It's symmetrical going left and right here, or up or down there, but the current leaving here is not going to be the same as the currents leaving right or left here. Now, with the current here, 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 and here being the same, then the potential difference going across this branch, this branch, this branch, and this branch are the same. So we now know that the potential, I'll designate it by a triangle, at these points are going to be the same. Those have to be at the same potential. So we have the same potential on here, we have the same potential there. Now, the potentials at this spot, this spot, this spot, and this spot have to be the same. I'll designate these with a purple X. By symmetry, those have to be the same potential. Now, as we move further out, we can make similar types of arguments. The current here is going to divide equally, going right or left. This current is going to divide, but it's not going to be the same as this current. And this current's going to divide equally, and the same there. But the current coming out in this direction is not going to be the same necessarily. So this current, this current, this current, by symmetry, are the same currents, but they're not the same as the other two currents that's leaving that particular node. Now, this potential at this spot, this spot, this spot, and this spot have to be the same. Now we can use similar types of arguments and look at the other nodes in here. We'll know that the potential here, we'll call this a square. Here, 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 this node, this node, this node, and this node have to have the same potential. This is much, you can think of this as being a sheet of current, a sheet of uniform resistance. Like if you had teledaltus paper, and say you had a uniform surface resistance on this sheet of paper and we eject a current into the center, this current's going to split and travel equally in all directions, radially. So for any particular radial distance out, we're going to have an equal potential. These will be equal potential lines. This is essentially going out to infinity. The potential on the rim will, out at infinity, will be 0. So this will have concentric circles of equal potential lines. So we can see that that same sort of thing is happening here. We can have a grid, since it's infinite, it's looking like a sheet of current or a sheet of resistance. So any point, any node that's equal distance in terms of counting horizontal and vertical grid lines to get a radial distance, any one of those points, nodes, will have the same potential. For example, we'll have the same potential at this spot as this spot, because we have 2 vertical grids, 2 horizontal grids. 2 vertical, 2 horizontal. Same thing here. We have, going from here, 2 vertical, 2 horizontal. So those points will have the same potential. And then we're going to find that we have, say, 1, 2, 3 vertical, 1, 2, 3 horizontal. So we'll have the same potential here. I'll call that a triangle with an X. So we'll have the same thing here. 1, 2, 3, 1, 2, 3. A triangle with an X. We'll have a triangle with an X there. Triangle with an X there. And then we'll have, say, at this point, well, let's go to this next one over. Let's call this a circle with an X. So we go 1, 2, 3, 1 over. So that will have the same potential. 1, 2, 3. See, we're going 1, 2, 3 down, 1 over horizontally. So we go 1, 2, or 1, 2, 3, and 1 over. So these will also have the same potential, and we'll have that one, and that one, that one, and that one. Then in between here, as we go from to this point, let's call this let's just use a different color so we can differentiate. I'll put this in purple. So we have 1, 2, 1, 2, 3. So I'll call this a purple square. This will be a purple square. This will. So we have the potentials, equal potentials, identified on this part of the grid, and we can keep using this similar sort of argument as we go progress further on through the grid. Now that we've identified similar potentials in the grid, let's see if we can simplify it by reducing it down and make now that we've identified similar potentials in the grid, let's see if we can reduce it down and simplify it a bit. In one of my previous lectures, I told you that if you have points in a network of equal potential, you can connect them with a short to simplify, because that won't change the potentials in the network at all. Because if we join similar potentials with a short, we haven't changed anything. Currents do not flow between 2 points of equal potential. So let's start here. We're injecting our current on this particular node. So we're starting here, and what do we have? We can connect these points here with a short. So what we have are 4 resistors in parallel. The resistors from this node to this node, we have 4 of them in parallel. So we can say we have a resistance, equivalent resistance of R over 4. And now we're at the red dot in the network. So I'll put that as our red dots. Now, moving on out, we see that the purple X's are at the same potential, so we can connect those with a short. Well, how many resistors do we have in parallel between the red node and the purple node? Well, we have 1, 2, 3, 4. So we have also an equivalent resistance of or no, not 4, but we have 8 of them. Counting from the red, we've got 1, 2, 3, 4, 5, 6, 7, 8. So there's R over 8. We have 8 resistors in parallel. So it's R over 8, and that's taking us to that node. Now, let's go from this node to the squares, to the blue squares, and find the equivalent resistance there. So now we're going to the blue square potential. Well, what do we have? We can connect the blues together as one node, since they're all at the same potential. So how many resistors do we have there? Well, going from the purple X to the blue, we have 1, 2, 3, 4, 5, 6, 7. We have 8. So it's R over 8 in parallel, going from the purple node to the blue node. How about now going to the green triangle? Well, I'm going to write that over here. Let's put our green triangle here and find the equivalent resistance between the blue node, square node, and the green triangle. Well, how many resistors do we have going between them? Well, we have 1, 2, 3, 4, 5, 6. Again, we have 8 resistors in parallel. So we can call this equivalent resistance R over 8. Now there's a path between the triangle and the red dot right here. So how many of these do we have? We have 1, 2, 3, 4 resistors in parallel. So we can write this as R over 4. Now, let's go from the blue square to the red with an X. So we're going to have our red circle with an X, and what's the equivalent resistance that we have there? Well, from the blue square to the red circle with an X, we have 1, 2, 3, 4, 5, 6, 7. Again, R over 8 is the equivalent resistance. We have 8 resistors in parallel. Now, let's go to, say, the yellow square, and connect those up. So these are at the same potential. So how many resistors do we have in parallel between that and the blue? Well, we don't have any. The blue has to go through 2 resistors, so the adjacent nodes are to the greens or to the red X's. So the yellows go to have a resistor that's connected to the red X's and has a resistance to the green. So we get those 2 equivalent resistance. So from the red X to the yellow square, we have 1, 2, 3, 4, 5, 6, 7, 8. So the equivalent resistance is R over 8. How about from the yellow square to the green square? There's 1, 2, 3, 4. So this is R over 4. Now let's go from the blue square to the red dot, or to the red circle. So we're going to go from the blue square to the red circle. What do we have going on there? Well, how many are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 resistors in parallel, so that's R over 8. And then we can go from these to, say, the purple square. Well, what do we have when we get the purple square? Well, purple square can go to the red circle with an X, and it also has a resistance going between it and the red circle. Well, what's the equivalent resistance? From the circle with an X to the purple nodes, we have 1, 2, 3, let's see here. We have 1, 2, 3, 4, 5, 6. We have 8 of them. So from the red circle with an X to the purple square, we have 8 resistors, so it's R over 8. How about from the purple square to just the circle? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. Again, R over 8. So you can see the method here. You can go out further on the grid, and now we have an equivalent circuit. And it should be immediately obvious now as to why you cannot invoke symmetry once you get beyond the first current split from where the current is injected. Remember, our current's being injected here. And the current splits 4 ways to get us through here. But once we get to the red node, so that we get to the next path to the X on the opposite diagonal, we see that we don't have symmetry. Okay? And we don't necessarily know what the potential difference is. If the potential here and here were the same, then we could get how the current split. It would be a 1/3, 1/3, or a 2/3, 1/3 type situation. We'd have 2/3 of the current going in here and 1/3 of the current going here, but we don't know that because we also have this resistance, so don't know what the potential here is in relationship to this potential. So we do not have symmetry. You can see that this current and this current are not going to be the same. They're not going to split equally. So hope that helps you understand the nature of this network and why you cannot invoke symmetry in the current splits once you get beyond the first division, because it will not satisfy Kirchhoff's current laws and voltage laws as you get further out into the network. I'll give you a hint to find the equivalent resistance between the two adjacent nodes. It is not a rational number. It turns out it's an irrational number. So if you end up getting the equivalent resistance as, if you say that between say this node and this node, if the equivalent resistance is Q times R, or Q is or P over Q times R, where P over Q are integers, that is not the correct answer, because P over Q, where P and Q are integers, is what we call a rational number, and this equivalent resistance is not a rational number. It cannot be expressed this way. So if you end up with, say, R over 16 or 3R over, say, 13 or something like that, that can't be the right answer because these are rational expressions. So hope that helps you out. Good luck. We'll keep the problem open until someone comes up with the correct answer.